So in this lecture, what I want to do is sort of make a little bit of a segue to really kind of touch on some of the things that I ended the previous lecture, part 1, with. And this is the topic of properties of this general set of integers modulo m. And it turns out that there's a very interesting field, a very important field in modern mathematics called abstract algebra, which really serves to generalize many concepts of operations on sets and operations between sets. What I'm going to do is I'll start off by giving a general overview of many of the different types of sets, and I should say sets with set operations that are discussed in abstract algebra, and then I'll give you a number of different examples of some of the most common ones. What I want to do is show how what we're doing right now really ties into abstract algebra. The main idea here is that if you have a set of mathematical objects, you typically are interested in the operation or various operations between objects in this set. And so we have something like this. We call it an algebraic structure, and we have many different examples, really, of a given algebraic structure. Anything that you're trying to model with set theory in certain relations like multiplication relation or addition relation can be modeled by some algebraic structure. And just to kind of show my point here, if we look at this listing of various algebraic structures, you can see very clearly that there are many different types of algebraic structures. And these all have very specific definitions, and there are essentially like an axiomatic definition for each one of these structures in terms of our propositional logic and in terms of our axiomatic set theory. Specifically, we're going to focus in this part of the lecture on what's called a group, and with that we'll also need a monoid to go over and define some of the other things we'll talk about in the lecture. We're going to break down the definition of a ring and give a lot of examples of a ring, just like we will give a lot of examples of a group. And we'll also need to talk about a semi-ring as well. And I'll also break down the definition of a field, because these things are essentially, the group is, we'll say the most basic, and I shouldn't say most basic, but the starting point in most abstract algebra courses. A ring would be maybe something that you would see in a second course on abstract algebra, and as well as a field in the second course. So typically you start with groups, study them for a long time, and then go to rings and semi-rings. Now, we won't be doing anything super advanced, but I will write down the definitions and kind of explain exactly what these are, so you can kind of get some context for the examples and where all of these examples fall into what we've been studying. I'm not going to write down the definition of a lattice now, but a Boolean algebra, which we're all very familiar with at this point, maybe not with the name, but with manipulating and and or operations on 0, 1 values, is directly associated with the lattice-like structure. Likewise, we're going to kind of see this by the end of the lecture today, where I'll kind of talk a little bit about all of these things. And so, starting with groups, or I should say group-like structures in general, listed before a number of different properties that the set Zm with addition plus modulo m satisfy. Turns out that group-like structures are going to be directly characterized by a lot of these similar properties, but in general. So a group we're going to be defining as something that's closed, which means the group operation between any two elements is another element in the group. The group operation will be associative. They'll exist in identity. In Zm, this is just 1. And we'll have invertibility in a group. So any element in the group, we can do the group operation with some other element, which is the inverse element, which will give us the identity of the group. What we're also going to see, and this is important for defining a ring, is that a monoid is like a group, but with the condition of invertibility removed. So we don't necessarily need to have inverses of elements in a monoid. And we have a nice diagram here that is expressing this. That's this right here. So as far as we're concerned, right, in this class and in this lecture, we're just going to be focusing on groups and monoids. But you can see that there's a lot of other algebraic structures as well that any combination of these properties or removal of these properties or addition of other properties will give us eventually, right, a group. But a group is when we have associativity, identity, and invertibility. If we remove the condition of invertibility, we're left with a monoid. So let's get down and write down the actual definition of the group and see some examples. And what I want to do is just write down here before we define a group is that typically in undergraduate abstract algebra sequence, you'd start out by going over and studying group theory, ring theory, and field theory. And each one of these is a very, very, very large topic in and of itself. But the idea here is that there are very, very rich mathematics and mathematical ideas contained in each one of these topics, with specific applications to computer science, to really many aspects of physics, modern physics, and also even in engineering. So the idea is that we're just going to, in this part of this lecture, just describe some of these algebraic structures and see how they tie in with what we've been talking about over the course, and specifically in respect to modular arithmetic. So we define a group G to be a set A together with a binary operation i.e. a function from the Cartesian product of A with itself back into A that satisfies the following three properties. First property is associativity. This is for all A, B, C in the group. We have that A and this binary operation. I'll just give a general name of star. This is a function with two inputs, input from A and an input from A, such that the result of the function is back in the set A itself. And I guess I want to point out here a little notation trick that we're going to do whenever you have a binary operation. Typically, instead of doing star of A, B, where A is an input from this set and B is an input from this set, we typically write A star B. So associativity is that A star B star C will be equal to A star B star C. Property of identity is the property that there exists in E in the group an element E called the identity element, such that A star E is equal to E star A, which is just equal to the element A itself. And lastly, we have an inverse element for any A in the group. There exists a B in the group such that A star B is equal to B star A, which is equal to the identity element of the group. Notation wise, sometimes and typically we denote this B by A with the -1 here, because this is similar to some ideas in linear algebra, and also similar to exponentiation of positive real numbers or positive rational numbers, and it's a very, very common notation. But don't be confused, right? If you see A with -1 there for a general group, it doesn't mean 1 over A, because in general, right, we can't define 1 over A for a general group. So I want to note here, right, that the closure that I talked about before, which is required for a group, is inherent in the fact that this binary operation is a function and not a partial function. So the idea here is that for any element in this set, and in this set we have that it's also an element in the set. So for any two inputs from A, when we put them into this binary operation, we're going to get another element in A. So the fact that this is a function is directly the reason why the closure condition is satisfied for the group. And then the other three conditions are associativity, identity, and invertibility. So on a note here, this is a notation thing. A group in which the operation star is commutative, or A star B is equal to B star A, is called an abelian group. Right, so if we have a set with a binary operation such that we have four axioms that hold, the fourth axiom being commutativity, then we say this group is a very special type of group called an abelian group. Not all groups are abelian groups, and it's very important that you realize this. However, abelian groups are very important to distinguish from a typical group because of the fact that they have very special properties, and they're actually used in the mathematical definition of more complicated algebraic structures. Another note here. You see that a monoid is a set A and a binary operation star that satisfies one and two above, but not 3. So we don't necessarily have inverse elements in a monoid. And so what I'll do right now is really list out a number of different examples, and I really think that it'd be good for you to go over a couple of these to really kind of like show that each one of these axioms makes sense in the sets. So in terms of just basic sets, we have that the integers with addition are a group. The identity element E is just the number integer 0 for any integer A. The inverse is negative A, and so on and so forth. We have that the set of rational numbers under addition is a group. The set of real numbers under addition is a group. The set of complex numbers under addition is a group, and so on and so forth. We have that the rational numbers minus 0, so without 0, is a group under multiplication. And I'll just put a box here next to each one of the examples. like I said, it'd be good for you to go through and verify that some of these basic examples are actual examples of groups. We have the set of real numbers, minus 0, so without 0, forms a group under multiplication. The set of complex numbers, minus 0 in the complex plane, so without 0, forms a group under multiplication. Complex multiplication, like this is complex addition, so on and so forth. So these are a lot of really good basic examples to go through and show. The cyclic group of order M is at this point really familiar to us. This is the set Zm in integer addition modulo M in this set. This is an abelian group. By the way, each one of these are also abelian groups. This is from the commutativity that gets is inherent with this modular arithmetic, as well as the commutativity that is inherent in all of the previous sets. And for this next example, I'm actually going to be very specific. I'm going to call it a non-example, because the following is a set of integers with normal integer multiplication is not a group. And it's not a group because there's no inverse elements, i.e. there exists no q in the integers such that p times q is equal to 1 for any p greater than 1. The identity element of this group, by the way, I'll be specific, it's the integer 1. Just like any of these multiplicative groups right here, the identity element is also 1 in each of the respective sets. In this set right here, the identity element is the integer 1, because 1 times any integer is equal to itself. And for any p greater than 1, there's no inverse element of p. Say, for example, p is equal to 2, right? For any k in z, we know that if k is 0, we get that 2 times 0 is equal to 0. K is 1, and 2 times 1 is equal to 2. If k is negative 1, then 2 times negative 1 is equal to negative 2. And for any other value, k times p is going to be either less than -1, strictly less than -1, or k times 2, or p is 2 here, is going to be strictly greater than +1. And because of this, there are no values of k that we can multiply by p to get the identity element 1, which means that this set is not a group. For another non-example, consider the set of natural numbers and addition. This is not a group. Remember, that natural numbers is 0, 1, 2, so on and so forth. Right? And there's no values that I can get such that in this set, such that for any p or for any n in the natural numbers, there exists no m in the natural numbers such that n plus m is equal to 0, where 0 is the identity element of this group. So because of the no inverse elements, this is not a group. However, each one of these is an example of a monoid, because addition in this case is associative in the natural numbers, multiplication is associative in the integers. For one final example, or I should say one final non-example, we take the integers modulo m with multiplication modulo m as our group operation, or as I should say as our binary operation. This set is not generally a group. And this might surprise you, because I'll give you an example of this. We take Z4, which is the set 0, 1, 2, 3. The element 2 has no inverse. The identity element of this group clearly is going to be the element 1. And we can very clearly see that 2 has no inverse, because if you take 2 times 0 mod 4, you get 0. 2 times 1 mod 4 is going to be equal to 2. 2 times 2 mod 4 is going to be equal to 4 mod 4, or 0. And 2 times 3 mod 4 is going to be equal to 6 mod 4, which is 2. So we very clearly see that 2 has no inverse. There's no element in this set of 4 elements such that the multiplication of 2 with this element is equal to 1, and therefore this is not a group. However, if we can consider another Subexample, take z5, 0, 1, 2, 3, 4. Z5 is in this set. This set of integers modulo 5 minus the 0 element with multiplication modulo 5 is a group. So if you think of what we have here, the group identity is 1, and 2 times 3 mod 5 is equal to 6 mod 5, which is 1. So 3 is the inverse of 2, and 2 is the inverse of 3. And 4 times 4 mod 5 is equal to 16 mod 5, which is also equal to 1. So the inverse of 4 in this set is just 4 itself. This is a special example of a group of integers, multiplicative group of integers, and it shows that even though this is not an example in general for certain integers, we actually end up getting a group structure with this modular multiplication. And what I want you to do is look at the differences between these two examples. The main difference here is that Z4, right, is a modular multiplicative, or a set with modular multiplication, but the number m in this example is not prime, whereas the number m in this example is prime. So in general, what we're going to show is that if we take the set of integers mod a prime number, that this set will be a group. If P is prime. This is a big theorem that we'll end up showing a little bit later on as we move a little bit further into modular arithmetic. Now I want to make an interesting point here. You'll notice that in the example that works, where Z5 is a group, well, Z5 isn't a group at all. Then what I've had to do was remove the 0 element from Z5 in order to make it a multiplicative group. So these values 1, 2, 3, and 4 are called units, or invertible elements that are non-zero in Z5. And even if you, say, remove 0 from Z4, this is still not a group, right, as this example right here that I showed. So it's really important to understand that and see that sometimes in order to make a group, and very often for multiplication, you have to remove the 0 element of the group. And what's interesting here is that what you have to remove is it actually is the additive identity for the additive group. So for this set right here, the additive identity for the rational numbers is the rational number 0, and we have to remove this from the rational numbers in order to make it a multiplicative group. Same thing for the real numbers, the complex numbers, and so on and so forth. So specifically in each one of these examples, the rational numbers with addition, the identity here is the rational number 0. Same thing for the real numbers and the complex numbers. In these new groups, though, when we remove 0 from the rational numbers, the identity element in the multiplicative group is 1, 1, and 1. This is a very interesting, and important point. So all of the examples shown so far have been commutative or abelian groups, because the order of the group operation doesn't matter in some sense. You get the same value for any order of multiplication. So what we're going to do now is see some more advanced examples of groups that are non-abelian, which are in some sense as important or more important in certain applications. These are non-commutative groups. Examples. So first we'll define notation mn parentheses R to be the set of m by n matrices with entries in the real numbers. And we'll see that we can actually extend this as well in general, but with this definition now, say that set mn of R, comma, addition, where addition is defined as the bitwise matrix addition that we defined before. This is a group. And this is actually an abelian group, because for any two matrices, A plus B equals B plus A. For multiplication, we have to be careful though. If I define a special set M bars here to be the set of all A in mnn of R, so all matrices A that are square, equal number of rows and columns with real entries, such that A is invertible, or there exists a matrix A inverse such that A times A inverse equals the identity matrix, then the set actually has this group has a special name. It's GL of n. This is the set M combined with the matrix multiplication. The operation here is matrix multiplication. So this is the group operation for this group, but GLN is a non-commutative or non-abelian group. It's possible to go through and show that matrix multiplication is associative, and because of our definition of M here, we have that an inverse for any element A always exists. In the identity element of this group is the identity matrix itself. But we have that A star B is not equal to B star A. And because of that, right, this is not, this group is not commutative. And this is the statement that A matrix multiplied by B is not in general equal to B times A for general elements in this this group. Another good example is called a permutation group. Think of G as the set if we suppose S is a set, and we consider the set of all bijections from S to itself, or more specifically, I'll call this set A, a set of all functions from S to itself, such that F is bijective, then G, or we consider this set A along with the function composition operation between function and this set, can be shown to be a group. Because it's relatively straightforward to go through and show that function composition is associative, and there's an identity element in this group, because you can just take the identity permutation, which is just each element mapping onto itself. That's the identity function. And lastly, right, any permutation, because we're dealing with bijections, can be reversed. So we can find, for any bijective function here from S to itself, or any permutation of the set S, we can always find a corresponding bijection that reverses this permutation. So the group operation here is function composition. And furthermore, if S is a finite set, with cardinality equal to n, then G is called the symmetric group on n elements. And when we get into counting, we'll actually show that there are n factorial elements in this group. And this is actually a relatively straightforward application of the product rule for counting from before. So this is a very special non-commutative group. And we can see that this is non-commutative, and also what the number of elements in the group are, if we just look at a set containing two elements, and we think of all bijections from S into itself. For this, you have that we call F identity to be the function that is the identity function, or that maps A to A and A to B. And then we'll say F1 is the function that maps A to B and B to A. And you can really see that this group is in fact obeying the fact that there are two elements in this group, or I should say 2 factorial elements in this group. Now F composed with F1 composed with F1 is equal to the identity mapping, right? So we can't really get a clear picture of how this is a non-commutative group in general, right? Because we really only have 2 elements in this group. The identity map composed with itself is just the identity map, and F1 composed with itself is just the identity map, and then F1 composed with the identity map is going to be equal to F1 itself. However, if we make this a little bit more complicated by considering the set of all functions from a set of 3 elements to itself, or this such that F is a bijection, the picture becomes a little bit more rich. We have the identity map still. We have F1, which takes A to B, B to A, and C to C. F2, which takes A to B, B to C, and C to A. F3, which takes B to B, A to C, and C to A. F4, which takes A to C, C to B, and B to A. And lastly, F5, which takes A to A, B to C, and C to B. Note that the number of elements in the set here is 3 factorial, or 1 times 2 times 3, which is 6. And if you go through and look at some of the compositions, you'll see very clearly that this group is not commutative, not abelian. And this is not abelian because F2 composed with F1 equals F3, but F1 composed with F2 equals F5. it's relatively straightforward to show this, right? For F1 maps A to B, F2 maps B to C, so F2 composed with F1 maps A to C, like in F3, F1 maps B to A, F2 maps A to B, so F2 composed with F1 maps B to B, and F1 maps C to C, and F2 maps C to A. So F2 composed with F1 maps C to A. This is equivalent to F3. But F1 composed with F2 is going to be F5, because F2 maps A to B, F1 maps B to A, so F1 composed with F2 maps A to A, maps F2 maps B to C, and then F1 maps C to C, so F2 maps B to C, or F1 composed with F2 maps B to C, and then F1 composed with F2 maps C to B, because it maps F2 maps C to A, F1 maps A to B, which is exactly the same thing as F5, which maps C to B. And as far as the counting rule is concerned, it's relatively straightforward to go through and show by induction that for a general finite set S of cardinality N, that the size of this group will be n factorial. And the idea here is that, well, we always have to choose a position for A, the first mapping, of which we have n possible positions to put A in. And we have n minus 1 choices for B, n minus 2 choices for C, and so on and so forth, all the way until we get down to the last element in our set. The second to last element will have 2 choices, and the last element we'll have to put in the only remaining slot. And by our product rule for counting, we clearly see that the multiplication of all of these numbers is going to give us the total number of possible functions in this set. So this is very neat. So for final example here, we'll consider what's called the free group on generators. And specifically, I'm going to consider the free group on 2 generators, but this can be relatively easily extended to the free group on any number of generators. And what we'd first do is define symbols, 2 symbols, A and B, and corresponding other symbols, A with a -1 and B with a -1. These do not mean inverses of A and B. We haven't defined any set or group. These are just symbols, A, B, A with a -1 above it, and B with a -1 above it. And we consider the set of all strings that are finite. So all finite strings that can be formed or generated by these symbols these finite strings can also be called finite words. Such that no A is directly next to and A with a -1 next to it, and no B is directly next to and B with a -1 next to it. So for example, just an example of an allowed string, we have A, B, A, B, -1, B, -1, A, B, and not allowed is A, A-1, B, 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 -1, A, B, A-1, A-1. And this is not allowed because of these two next to one another and these two next to one another. The group operation star is string concatenation, or joining of strings with removal of all pairs of the form A-1, A-1A, B, B-1, or B-1B. So for example, AB, AB-1 with BA, A, B-1, A-1 is going to be equal to ABA, AA, B-1, A-1. And this is a super important group for a number of different reasons, but hopefully you can see the important connection here to computer science and computer code, where you have any given code is going to have a finite number of symbols, and the set of all possible words that you can form from that code are going to be directly related to this group in some sense. This group has many other important applications to computer science, but also to, not just to computer science, but also to many areas of other areas of mathematics, such as topology. It can be used to prove the Banach-Tarski paradox. There are an extremely large number of applications of this group.